Right now, while your engine seems to be running fine, there could be a single dirt-clogged sensor that's destroying power output, increasing fuel consumption, and shortening engine lifespan, all without triggering a single dashboard warning light. How is it possible that a finger-sized component can make a car feel sluggish, burn through more gas, and fail emissions testing all at once? Trustworthy mechanics see the same pattern daily. They replace spark plugs, ignition coils, even the fuel pump. Yet the issue persists until they clean a sensor that hardly anyone touches. And no, it's not the one most people think of. There's a hidden culprit that builds up grime over years, sends false data to the computer, and turns any healthy vehicle into a chronically sick one. Throughout this video, we'll break down the most problematic sensors one by one, but the one that fails most often, the one almost nobody cleans and that can transform engine behavior in minutes, will only be revealed at the end. Number 13. MF Sensor. Mass Airflow. The mass airflow sensor stands as one of the most critical yet simultaneously most overlooked components in electronic fuel injection systems, responsible for measuring with microscopic precision every gram of air entering the engine. This device uses an extremely thin platinum wire, roughly the thickness of a human hair, that's electrically heated to a constant temperature while passing air cools it proportionally to flow velocity. What's actually happening is the computer measures the electrical current needed to keep that wire at stable temperature, translating that data into air mass with millisecond precision. The devastating problem appears when microscopic dust particles, vaporized oil from reusable air filters, or environmental contaminants settle onto that sensitive wire, completely altering its thermal properties. The computer starts receiving incorrect information about actual incoming air volume, responding with inappropriate fuel mixtures that generate confusing symptoms: power loss during hard acceleration, elevated fuel consumption without apparent reason, irregular idle that randomly improves and worsens, and in extreme cases, the engine stalls completely when decelerating sharply. In diagnostic shops, approximately 40% of vehicles with lean or rich mixture codes have contaminated, not defective, airflow sensors. Cleaning requires specific mass airflow sensor cleaner spray and a delicate technique that avoids physically touching the sensitive element. But there's another air measurement sensor with completely different technology. Number 12. MAP Sensor. Manifold Pressure. The Manifold Absolute Pressure Sensor represents alternative technology for measuring engine load, primarily used in vehicles equipped with speed density injection systems that don't require a mass airflow sensor. This component directly measures vacuum or positive pressure inside the intake manifold through a piezoresistive element that changes electrical resistance proportionally to atmospheric pressure applied to its surface. What this sensor does is translate engine load into electrical signal. When the throttle is closed and the engine operates at idle, manifold vacuum is high and the sensor reports low absolute pressure values, typically between 20 and 30 kPa. During full throttle acceleration, vacuum disappears and pressure equalizes with atmospheric, reaching values near 100 kPa at sea level. The computer uses this information along with temperature and RPM data to calculate incoming air mass through complex thermodynamic formulas. The critical problem arises when vacuum hoses connecting the sensor to the manifold develop microscopic cracks or partially disconnect, allowing leaks that completely distort readings. The sensor reports lower vacuum values than reality, making the computer assume higher engine load and inject excessive fuel. Symptoms include skyrocketing consumption, black exhaust smoke, and persistent rich mixture codes. In shops, cleaning the sensor connection port and verifying hose integrity resolves 80% of problems attributed to this component. But there's an even more critical sensor that directly affects emissions. Number 11. Oxygen Sensor. Lambda. Oxygen sensors installed in the exhaust system are the computer's eyes for constantly monitoring combustion efficiency and dynamically adjusting air-fuel mixture thousands of times per minute. These devices function through a zirconia ceramic element heated above 300 degrees C that generates voltage when detecting differences in oxygen concentration between exhaust gases and outside atmospheric air. An engine operating at ideal stoichiometric mixture of 14. 7 parts air to 1 part, gasoline produces exhaust gases with minimal residual oxygen, causing the sensor to generate approximately 0.455. When mixture becomes lean and unburned oxygen increases, voltage drops below 0.3 V, a signal the computer interprets as needing to add more fuel. The opposite occurs with rich mixtures where the sensor generates voltages above 0.6 V. The devastating problem appears when sensors become contaminated with deposits of lead, silicone, or phosphorus from low-quality fuels, or burned oils entering the combustion chamber through worn rings. These contaminants chemically poison the zirconia element, reducing its sensitivity and response speed to the point where the sensor sends sluggish signals the computer can't effectively use. The result is slow oscillations between rich and lean mixture, elevated fuel consumption, noticeable power loss, and guaranteed emissions test failure. However, there's a position sensor whose failure generates completely different symptoms. Number 10. TPS, Throttle Position Sensor. The throttle position sensor is a precision potentiometer mounted directly on the throttle butterfly shaft that informs the computer of the exact opening angle the driver is requesting at every moment. This simple but critical component contains a circular resistive track over which slides a moving contact that divides reference voltage proportionally to angular position, typically generating between 0.5 V with throttle completely closed up to 4.5 ohc at maximum acceleration. What the computer does with this information is fundamentally important. It determines whether the driver is accelerating smoothly requiring economical mixture, or flooring it demanding maximum power with enriched mixture and aggressive ignition advance. The critical problem appears when the sensor's internal resistive track develops worn or contaminated zones, creating dead spots where voltage momentarily interrupts or fluctuates erratically. These dead spots typically appear at most used positions corresponding to highway cruise speed or elevated idle in urban traffic. What the driver experiences are jerky accelerations, momentary power loss at specific pedal positions, even complete engine shutoffs when the throttle passes through those defective zones. In diagnostic shops, technicians verify the sensor by monitoring its voltage signal with a scanner while slowly moving the throttle, looking for jumps or abrupt drops indicating internal potentiometer wear. Number 9. CKP, Crankshaft Position Sensor. Without the crankshaft position sensor, a modern engine is literally blind. This small component mounted very close to the flywheel, or a toothed wheel, with notches on the crankshaft sends a series of perfectly synchronized electrical pulses each time teeth pass in front of its magnetic tip. What's really happening is the computer uses those pulses to know exactly where each piston is at all times and how fast the engine is spinning, calculating the precise moment to inject fuel and fire the spark. When the sensor starts filling with metal filings, burned oil, or dirt, the signal becomes distorted and intermittent failures appear. The engine shuts off when hot without explanation, takes longer to start, or loses spark for fractions of a second while driving. In shops, mechanics constantly observe how a simple cleaning of the sensor tip, removing metallic debris with a clean cloth and contact cleaner, returns total stability to engines that seem to have serious ignition or fuel pump failures. But the computer doesn't just need to know crankshaft position. It must also precisely know what the camshaft is doing. Number 8. CMP, Camshaft Position Sensor. The camshaft position sensor works alongside the crankshaft sensor like two perfectly coordinated clocks. While the crankshaft sensor tells the computer engine speed and general position, the camshaft sensor reveals exactly which phase of the cycle each cylinder is in, allowing precise sequential injection and synchronization with variable valve timing systems. This sensor is usually mounted in the timing cover or directly on the cylinder head, reading a tone wheel or metal protrusion on the camshaft. What it really does is send a unique reference per cam rotation, marking cylinder number 1 at its combustion point. When it starts failing due to dirt, thick oil, or internal cracks, the computer loses that fine reference and enters degraded mode. It switches from sequential injection to batch injection. Idle becomes unstable and cold starts to take longer and become more hesitant. Many engines show smooth hesitations between 2,000 and 3,000 RPM that are incorrectly attributed to coils or injectors, when actually a contaminated camshaft sensor is sending weak or deformed signals. A visual inspection and cleaning of its reading zone can make an enormous difference in running smoothness. But there are even more ignored sensors that get dirty with simple air passage. Number 7. IAT, Intake Air Temperature Sensor. The intake air temperature sensor is usually a small component bolted to the intake manifold or integrated into the air filter duct. so discreet that most drivers don't even know it exists. Its function seems simple: measure how cold or hot the air entering the engine is. However, what's really occurring is fundamental for fuel mixture. Cold air is denser and contains more oxygen per liter, while hot air is less dense. The computer uses this sensor's reading to adjust how much gasoline to inject each cycle. When the sensor gets covered with nebulized oil, stuck dust, or residue from oiled air filters, its internal thermistor no longer correctly senses actual airflow temperature. The result is an artificially hotter or colder reading than reality, making the engine run slightly rich or lean all the time. This translates to smooth but constant power loss, elevated fuel consumption, and, in some cases, light detonation in very hot climates. Technicians observe that careful cleaning with electronic cleaner without touching the sensitive element returns quick sensor response and stabilizes mixture. But there's another thermal sensor controlling something even more critical: the temperature of the engine's very heart. Number 6. ECT. Engine Coolant Temperature Sensor. The engine coolant temperature sensor is a thermistor immersed directly in the cooling system that tells the computer how hot the engine block is running. This sensor is critical because the computer uses it to determine whether the engine is cold and needs enriched startup mixture, warming up and requires gradual adjustment, or at operating temperature and can run at peak efficiency. What's really happening is that when the engine is cold, this sensor has high resistance sending low voltage signal. As coolant heats up, resistance drops and voltage rises, informing the computer that combustion chambers are reaching optimal temperature. The problem appears when the sensor gets covered with coolant deposits, corrosion, or electrical contact deterioration. It starts sending false readings. The computer thinks the engine is cold when it's hot, or vice versa. The result is hard starting, rough cold idle, excessive fuel consumption during warm-up, or even overheating without warning. In shops, technicians see engines running permanently rich because a contaminated coolant sensor falsely reports low temperature, making the computer inject as if it's perpetually cold. Simple sensor cleaning or replacement transforms engine behavior completely. Number 5. VSS. Vehicle Speed Sensor. When the speedometer starts dancing, the transmission makes weird shifts, or cruise control deactivates for no reason. Many times the silent culprit is the vehicle speed sensor. This sensor, generally mounted in the transmission case or differential, sends electrical pulses proportional to actual wheel or output shaft rotation speed. What's really happening is each of those pulses translates into data the computer uses to know how fast the vehicle is traveling, when to shift gears, how to adjust mixture during deceleration, and when to activate functions like stability control. When the sensor gets contaminated with oil, sludge, metal filings, or road dirt, its signal becomes distorted. Pulses arrive incomplete or irregular, and the computer believes the vehicle is going faster, slower, or even stopped when still moving. In shops, mechanics observe that simple VSS cleaning, removing metallic debris stuck to its magnetic tip and cleaning the connector with contact spray, returns stable reading and eliminates erratic gear changes many confuse with serious transmission failures. However, there's an even more critical sensor that listens to the engine interior like a high-precision microphone. Number 4. Knock Sensor. Inside the engine block exists a microphone bolted directly to the engine body that permanently listens to every explosion in the cylinders. It's the knock sensor designed to detect specific vibrations produced by rod knock or abnormal mixture detonation. What's really occurring is this piezoelectric sensor converts mechanical vibrations into electrical signals. The computer analyzes in real time to know if the engine is starting to knock due to low-quality fuel, excessive temperature, or aggressive ignition advance. When it detects knock, the computer acts in milliseconds, retarding ignition timing and slightly enriching mixture to protect the engine. The problem appears when the sensor gets covered with dirt, rust, dried oil, or is tightened with incorrect torque. It loses sensitivity and stops precisely transmitting those specific vibrations. The result is doubly dangerous. Either the computer doesn't detect actual knock and the engine works on the edge of damage, or false signals appear forcing the computer to constantly retard timing, robbing power and making the vehicle feel heavy and weak. Simple cleaning of the contact surface and connector along with proper torque wear when reinstalling usually completely transforms behavior of engines that seem tired. But there are sensors that don't protect. They warn when it's almost too late. Number 3. Oil Pressure Sensor. The red oil light on the dashboard is one of the most feared warnings for any driver, and behind that signal usually sits a small pressure sensor that rarely receives attention until something fails. This sensor is threaded into an oil passage in the block or cylinder head, and its function is simple but critical. Detect if lubrication system pressure drops below a safe threshold. What occurs internally is a diaphragm or sensitive element deforms with oil pressure and closes or opens an electrical circuit or generates proportional signal in more advanced systems. The problem is that over time, the sensor's inlet channels can fill with sludge, varnish from burned oil, or particles, creating a small plug preventing actual pressure from reaching the diaphragm. In that scenario, the engine might be working with dangerously low pressure while the sensor believes everything is normal, or the reverse, marking false alarms because response becomes slow and irregular. In shops, technicians have found clogged sensors showing perfect pressure on the dashboard, while an external gauge reveals critically low values. That's why cleaning or replacing this sensor during major maintenance can mark the difference between a protected engine and one walking toward catastrophic failure. But there's another apparently harmless gauge that also frequently deceives. Number 2. Fuel level sensor. The gas gauge on the dashboard seems a minor detail until one day the vehicle stops on the highway still showing a quarter tank. Behind that lying needle is the fuel sender, or float assembly, a level sensor living submerged inside the tank that almost nobody cleans or checks throughout the automobile's entire useful life. This system works through a mechanical float attached to an arm that slides over a variable resistor, changing electrical value according to float position in the fuel. What's really occurring is the computer or instrument cluster itself converts that resistance into the level reading the driver sees. Over years, the resistive track contacts sulfate, fill with varnish from poor quality fuels, or dirt deposits form, creating false dead spots. The result is gauges that dance, stick at half tank, or take forever to react after refueling. In specialized shops, technicians disassemble these modules, carefully clean tracks and contacts with specific cleaner, and verify smooth float movement. Many complaints of burns too much gas start with a lying level sensor. However, having perfect sensors means little if what fails is the nervous system connecting them. Number 1. Sensor connectors and electrical harness. In many complex diagnoses, hundreds of dollars get spent replacing defective sensors when the true culprit isn't the sensor, but the connectors and electrical harness feeding it. Each sensor depends on 3 fundamental things: correct power supply, solid ground, and clean signal reaching the computer. What's really happening in millions of vehicles with years of use is vibrations, humidity, engine heat, and small impacts slowly damage wires, pins, and terminals. Green sulfation forms in connectors, intermittent false contacts occur, wires half-cut inside insulation, and loose grounds come and go with each bump. Codes appear on the scanner pointing to temperature sensors, oxygen sensors, position sensors, or pressure sensors. But in the shop, mechanics observe that lightly moving the harness makes the fault appear and disappear. The fact most drivers never see is that simple, deep cleaning of connectors with dielectric cleaner, ground correction, repair of poorly done splices, and proper harness securing eliminates faults seeming like electronic ghosts. That's why the most experienced technicians always check harness and connectors first before condemning an expensive sensor. Because many times the problem isn't in the component, but in the path communicating its information.